this energy region in the band gap. Okay, in order for electron to essentially move in the semiconductor, it has to go up to the conduction band, okay, the empty state. And once you get up there, you can actually move freely in the semiconductor. And we kind of mentioned that there are actually two carrier type in the semiconductor, the electron, which is something that is not unfamiliar to you. And in fact, there's another carrier type that is called a hole. Okay, the charge is of the same magnitude as electron, except that it's positively charged. Okay, so in a semiconductor, actually these two types of carrier helps to carry current. Okay, when you apply a voltage in a semiconductor. Okay, so there's actually two carrier participating in current conduction. All right. Now we also mentioned that semiconductor can be broadly classified into two categories depending on the number of elements that is used in the semiconductor. The elemental type are those that have only one element type in the semiconductor. Okay, so materials like silicon or germanium semiconductor. Okay, these are considered elemental semiconductor material. Those that contains more than one element, okay, two and above, are considered compound semiconductor materials. Okay, so things like gallium arsenide, right, or indium phosphide, gallium nitride. Okay, there can also be 3 to 4 elements that are being used. So it depends on what sort of property you need for your application, and generally you choose those that suit your specific application. Okay, we also cover about this description of crystals. Okay, we mentioned about this lattice structure. Okay, we understand it as a framework of points in space, right? Where if you put atoms at the lattice points, you can create the semiconductor crystal. Okay, and in this lattice structure, okay, we can actually identify representative regions or representative units, which if you duplicate them and stick them together, right, you get back the semiconductor crystal structure. Okay, and as you can see here, there is actually many different ones that we can identify. So each of these are called unit cell. Okay, the smallest one is known as primitive cells. Okay, the smallest that you can identify are called primitive cells. So like the cell C and D are known as primitive cells. Okay, because that's the smallest we can identify to sort of duplicate and recreate the structure. So in order to describe semiconductor crystal, there's actually two quantities that we need to know how to define. Okay, one is the crystal direction, the other is the crystal plane. Okay, crystal direction is probably something that it's quite straightforward in the sense that it's essentially vectorial direction in the crystal. Okay, so the definition of it is really the same as how you describe a vector direction. Of course, the only difference is that for crystal direction, we define it or we describe it using square brackets. Okay, to define the vector direction. For planes, it's using a quantity called the Miller indices, and we have actually described the procedure for finding the Miller indices. The Miller indices is essentially a normal vector to the crystal plane. Okay, so it's still a vector quantity, sort of, but we distinguish it from the vector direction or the crystal direction using a different notation for the bracket. Right, for planes we use a round bracket. For crystal directions, we use a square bracket. Okay, that's the only difference we use, or the only way that we can sort of classify between directions or planes. Okay, so the basic building block of crystals, right, of all the crystals that you can find on Earth, right, out of the 14 different types that you can use, 3 of them are actually crystal lattice that is cubic. Okay, so in other words, the basic unit, right, the unit cell is in the form of a cube. Okay, so the length of the 3 sides are all equal, and the simplest one is a simple cubic where you have lattice points at the corners of the cube, followed by the body center cubic. Okay, in addition to those at the corners, you have one in the body and the face center cubic structure. Okay, that's the one with additional points in the center of each face. Okay, in the case of semiconductor that we deal with a lot, okay, the common semiconductors, a lot of them are actually face center cubic structure. Okay, the basic structure is actually a face center cubic one. So if you look at the silicon crystal structure, right, we see that you actually have those atoms at the corners and the center of each face, and in addition, there's actually 4 in the body. And essentially like that is because in the case of the phase array qubit structure, to get the silicon structure, right, we actually put not just one atom at the lattice points, but we actually put bases of 2 atoms. Okay, that is this two pair here, or this pair here with 2 atoms, right? You put this at each of lattice point, and you actually get this silicon unit cell. All right. Okay, so that's the basic structure for silicon, and we call this a diamond crystal structure. Okay. Right. So last lecture, right, we also kind of talk about very briefly this energy splitting, okay, in your semiconductor crystal, which leads to the band structure that we see earlier. So we started a discussion by first discussing about hydrogen atoms, okay, and hydrogen atoms, if you put them together into a molecule, okay, there's actually this energy splitting effect to accommodate the 2 electrons that initially have the same state, okay, because in quantum mechanics, that's actually forbidden. So by the same mechanism, you find that when you put a lot of silicon atoms together to form the crystal, okay, the the band structure itself actually would split, okay, will split in order to accommodate now this large collection of silicon atoms with a lot of electrons, okay, sharing the same state. So in order to accommodate it, they have to split, okay, and as a result, from our discussion, we see that the initial discrete levels for a single atom now basically splits, and you get this upper band and the lower band. Okay, and that basically forms your band structure of the semiconductor material. Okay, and it's essentially this part here at the equilibrium spacing that we have the band structure that we usually will use to analyze a semiconductor material. Okay, so the bottom of the conduction band edge is conventionally indicated as EC, and the top of the valence band is indicated as EV. Okay, and as I mentioned before, this gap here is specified as EG. The mechanism to create free carriers in a semiconductor essentially comes from taking an electron out from the covalent bonding, okay, which will give you a free electron that can move, and at the same time it leaves behind a vacancy, which is the hole that can also move by having electrons from a neighboring bonding breaking off to take its place, and you get the vacancy moving to another location. Okay, so in the band diagram, okay, this translates to an electron in the conduction band when it becomes free to move, and a hole in the valence band. Okay, so if you see an electron in the conduction band, then you should know straight away that this guy can move freely. Okay, it corresponds to a free electron that can move freely in the silicon crystal. In the case of the hole, okay, if you see a hole in the valence band, then this will imply that it's basically a carrier that can move freely in the crystal as well. Okay, so these are 2 carriers that can conduct current. So how do we get an electron out from the bonding? We mentioned 2 mechanisms. One, of course, is to increase the temperature of the semiconductor, where you provide energy, right, in terms of heat, and some electrons may gain enough to break off from the bonding, right? Similarly, you can also use light. Okay, if you use light of suitable energy, right, you can also take out an electron from the bonding to give you this free electron and a hole. Okay, so collectively, this electron and hole that's created, okay, are known as electron hole pairs. Okay, and in a pure semiconductor, you find that wherever you take out an electron, you always get a hole that is produced. Okay, so the electron hole pairs are always created, together, right? So wherever you have an electron that is generated, you get a hole that is produced as well. So they're always created in pair. In the case of pure semiconductor, right? In the case of the band diagram, I think one thing that you should also take note is that the energy band diagram is a plot of energy of electron. Okay, the vertical axis actually is the energy of electrons. In other words, if you go vertical, okay, the vertical shows increasing energy of electrons. Okay, in the case of holes, because it's positively charged, okay, if you look at the holes, right, the increasing energy for holes is actually downwards. Okay, so to a hole, if you go downwards, it's actually increasing in energy. So it's opposite, because the charge is different. So the way to understand this, sort of conceptually, right, is to think of the hole as like a bubble. Okay, so naturally, if there's some position in the valence band edge, then the hole will tend to go down to that position, right? Because remember, any particle always go to the lowest energy possible. So in the case of holes, the lower energy is actually going up. Okay, so you can think of the hole as like a bubble. Okay, so if the hole actually moves downwards, then it's actually going up in energy. So if you think of the case of bubble, you want to push it down, you need to exert energy to push it down, right? Okay, so conceptually, if you want to understand, you can think of hole as a bubble. Okay, then the electron is just like a regular particle, okay, in the energy band diagram. So, right. Okay, sorry. Okay, so other than this process where electron and holes are being created, that's called a generation process because they generate free carriers, okay? In a semiconductor, you also have another countering process called the recombination process that would cancel out the electrons and holes. Okay, so physically, you can think of it as electron moving in a semiconductor when it's free to move, right? And if it actually sees a hole, there's a chance that it could go back to the hole and complete the bonding, right? Complete the valence bonding. So if it does that, then the electron and holes will disappear. Okay, so this process is also ongoing, and you find that under steady state or thermal equilibrium condition, right, the generation rate and the recombination rate will balance. Okay, and what that means is that you actually see a stable number of electrons and holes in the conduction and the valence band in the valence band of the semiconductor. Okay, so under sort of equilibrium condition, the number of electrons and holes are stable. Okay, but of course, bear in mind that this is a dynamic process. The electrons and holes that is there, right, the stable number, they are always comprised of different electrons and holes. Okay, because they recombine, they get generated. They recombine, they generate. Okay, so the electrons itself, it's actually recombining and generating. So you're not seeing the same electron all the time. Okay, because some would recombine, some new one get generated. Okay, but the number is stable under equilibrium condition. All right. Okay, so for today's discussion, we're going to talk about the more in-depth on the energy band structure of the semiconductor. Okay, and what do we mean by that? So we start off with looking at like classical physics or classical mechanics. Okay, if you consider a free particle like a ball, and let's say this ball has a mass of m and it's moving with velocity of v, we can write down the momentum of this particle as mv, right? Okay, the momentum is given as the product of the mass and the velocity. We can rewrite this, okay, to relate this to the kinetic energy of the free particle. Okay, if your kinetic energy of free particle is half mv squared, we can write it in terms of the momentum. Okay, because we know that momentum is mv, so we replace the v with p. If you work it out, you get p squared over 2m. Okay, so in other words, there's actually a parabolic relation between the kinetic energy of this classical particle versus the momentum. All right, it's a quadratic relation. So if you draw a curve of energy against momentum, you actually get this parabola. Right? Make sense? Okay, that's a quadratic equation. So there's a parabolic relation between the kinetic energy and the momentum of the classical particle. Okay. So I'm not sure whether like all of you all have covered this in your H2 physics, electrostatic. Have you all learned Coulomb's law? Anyone?
Yeah.
Yes. Okay.
Yes.
Not yet. Okay.
No.
If I'm not wrong, this should still be in the syllabus, right? Yeah, this should still be in the syllabus. Anyway, so it's probably useful for me to just quickly run through because some of it we'll be using. Okay, so we look at electrostatic. In this case, suppose I have two positive charge, okay, with a charge value of Q1 and Q2, and let's say they're separated by a distance of R. So you know generally that if you have two positive charge that's close together, they will tend to repel each other, right? So under this Coulomb's law, right, the force, okay, that is acted on these two particles because of their charge that repels them, okay, the force will be F, is described by this equation here. Okay, it's actually proportional to the product of the charge of each of these particles, Q1, Q2, and divided by the square of the separation between them, R square. This 1/4 pi epsilon are constant. Okay, the epsilon is a permittivity of the environment that the charge is in. Okay, and of course pi, you know, it's 3.042, right? Okay, so the force that exerts on each of these particles is proportional to the product of their charge divided by the square of their separation. Okay, that's Coulomb's law. If you look at it, actually, it's kind of quite similar to gravitational law, right? Where if you have two mass, I'm not sure if you learned this, if you have two mass object, you put them at some separation, there's actually this gravitational force that will pull them together. And this gravitational force is actually proportional to the product of their mass and divided by the square of the separation. Okay, it's inversely proportional to the square of the separation. So the Coulomb's law actually have a similar expression, right? Except that here we are looking at the charge of the particle. Okay, and if you have a force quantity, we can actually work out the potential energy, right? The electric potential energy of one charge with respect to the other. And this is essentially proportional to the product of their charge, Q1, Q2, and inversely proportional to the separation between them. Okay, so it's actually a 1/R relation, right? Okay, it's a 1/R relation. So if we look at the case of an atom, okay, like a nucleus with some numbers of protons positively charged, and say I want to sketch the potential energy of these electrons in the field of this positive charge in the nucleus, right? You know that it is inversely proportional to the separation, right? If you sketch it, then you get this 1/R relation on both sides. Okay, so that's the potential energy of this electron in the vicinity of the nucleus in the atom. Okay, that's under electrostatic. All right. So then the question is, what about in the case of electron in a semiconductor, right? So if you think about it, electron in a semiconductor, it's kind of a similar problem, right? Essentially, a electron, one negative charge, and then you have this array of positive charge nucleus, okay, that the electron will experience. So what sort of potential energy or kinetic energy, what sort of potential energy will this electron have, in terms of how it can move, right? Or the kinetic energy. So this is essentially called the EK relation in the case of semiconductor, right? We're interested to know what is the EK relation of electron in a semiconductor. Very similar to that of the free particle, right? If you think about it, E to P, right? That's energy against momentum. In a semiconductor context, the energy against the momentum, right, is the EK. K is actually related to momentum in quantum mechanics, right? K is like a momentum quantity. So in semiconductor, we're interested to know what is this relation. Because if you know this relation, then you know how the electron will move, right, when it has some velocity in the semiconductor. Very much similar to, like in the case of free particle, if you know the kinetic energy against the momentum relation, you know how this classical particle will move. Like with certain velocity, it has a certain energy, right? That's kind of telling how it's moving, right, in classical sense. So in semiconductor, the EK relation actually allows you to describe the movement of the electron in the semiconductor. Okay, and so here, before we talk about the energy against the momentum relation of a crystal, let's look at a simple setup first, like a single atom. Okay, and let's try and see whether we can derive the EK relation for an electron around a single atom. Okay, so of course, if you look at a single atom, you have the nucleus, right? And we're interested to see the behavior of this electron around it. Okay, so the potential energy, right? The potential energy that the electron experience is essentially this 1/r relation, right? That's the potential energy that electron experience around the nucleus. Okay, as I mentioned before, according to electrostatic, the potential energy is a 1/r relation. Okay, so if you have electron around a nucleus positively charged, that's the potential energy that the electron will experience. All right. Okay. But of course, the thing is, if you want to use this, then actually it is rather complex. If you use this 1/r relation. Okay, and so in order to simplify this, we can actually use approximate representation. Okay, if you look at this 1/r relation, we can kind of imagine this as like a rectangular sort of well structure, right? You know, we can approximate like a well structure. So this actually has advantage of being a lot simpler because it's just a constant value, it doesn't change with R. Okay, and if you want to derive the EK relation, you use this representation. The equation that we're going to use will be easier to solve. Okay, so we can actually do this approximation. So if we do that, we can kind of represent it using this approximate representation, right? Where we define three regions. The middle one is kind of like the approximate region where it corresponds to the region where electron is sort of mostly there, and the outer region is the part where it's harder for electrons to go out to. Okay, because if you think about it, in the case of electron in an atom, right, without external energy, they tend to occupy the innermost shell, right, the lowest energy level possible, and the outer one, the chance of them being there is a lot less. Okay, so we represent it with this constant value here, V0. Okay, this is an approximation. This helps with solving equation. So in order to find the EK relation, essentially for quantum mechanical particle like electron, remember we have to use the Schrödinger equation. Okay, you cannot use Newtonian mechanics anymore. Okay, because you go to that small scale, the Newton's law and all that doesn't work anymore. Okay, it doesn't work accurately. So we have to use quantum mechanical equation, Schrödinger equation, to solve for this. Okay, and if you recall, in the Schrödinger equation, there is actually a potential energy term that we need to know. Okay, that's why here we have to first define the potential energy that is experienced by the electron, and then approximating it to a simpler form, so that when you put it in the Schrödinger equation, it's easier to solve. Okay, so if you do that, right, and you plug it into this Schrödinger equation, we can basically try and solve it now. So if you define the well region where the electrons is mostly there, right? Suppose we define that as V equals 0, and if we solve for this Schrödinger equation in this region, then we set this V psi to 0, right? And that gives us a simplified form, okay, for the Schrödinger equation. And in fact, if we consider just kind of like one-dimension problem, in fact, this Schrödinger equation, right? Remember the Schrödinger equation, it's like a del square of psi. Remember I said this del is like a derivative term. Okay, so in a one-dimensional problem, if you just consider like x-axis, okay, then this operator del, okay, is simply just a second derivative of your wave function. Okay, that's why we are sort of using second derivative of wave function here. And in fact, this equation here, in a one-dimensional case, it's a rather simple differential equation, second order differential equation that you need to solve. Okay, so you can actually get some analytical expression for this. And of course, in order to solve this, right, we are solving for the psi value, the wave function, and the energy term. Okay, these are two things that we need to solve in the Schrödinger equation. To solve this, of course, we can use some conditions from the case of the atom. First of all, a boundary condition where at the boundary of the well, right? So we look at the boundary here, we define one end as x equals 0, the other end as x equal to lx. and this two region corresponds to region where if you go beyond, okay, if you set this to infinity sort of potential energy, that means it's very difficult to get to, right? Then the chance of finding an electron at this edge will be 0. Okay, either x equals to 0 or x equals to Lx. So we can use this as a boundary condition to solve for a specific solution, right? This is kind of like a boundary condition that we can use, where the wave function will be equal to 0, meaning that the probability of finding electron at the edge or beyond is actually 0. Okay, remember the wave function, if you take the magnitude square, it gives you the probability of finding an electron at that position, right? So if it's equal to 0, that means there's no chance of finding an electron there. Okay. Then the other condition that we can use is that because the potential at the edge is infinity, so literally an electron in it will be bound to this region, right? Because this goes to infinity, there's no chance that you can find an electron outside. Okay, because it's so high, right? That electron, there's no way you can get out. Okay. So the other condition you can use to solve the Schrödinger equation is this. If you sum out all the probability of finding electrons within the well from 0 to L, right? So if you do a summation, that translates to the integration, right? If you think about it, the integration sign is like a summation. Okay, so here when we do an integration, we are kind of summing up all the probability of finding electrons from x equal to 0 to x equal to L, and this probability will be equal to 1 or 100%. Okay, because if the electron is confined within the well, you cannot find it outside, then the chance of finding the electron in the well is 100%, right? They are always in the well. Okay, so that's the other condition that we can use to solve for a specific solution in the Schrödinger equation. Okay, so if you do that, right? If you do that, again here you don't have to worry about how to get to this solution, right? This part here, we're not expecting you to be able to solve it, but just appreciate where it's coming from. So if you do solve it, if you can solve it, right, the Schrödinger equation, which is effectively a second order differential equation, then you get in fact this very simplified analytical expression. You find the wave function is actually a sine curve, right? And you have this k of x, which is what we call the wave vector. Okay, the wave vector is defined here. Okay, this comes from solving the Schrödinger equation, right? Once you solve it, this is the solutions that you will get. So the wave vector is given by pi nx over Lx. Remember, Lx is the dimension of the well, right? And nx here is some integer value, positive integer value, right? And okay, maybe not positive, it's just integer value, like it can be negative actually. And this wave vector, you can think of it as like a vector direction for the electron. Okay, so this n is some integer values, and so which means that k can be a range of integer values. All right, and which means that the wave function, right, there can be many different solutions depending on what is the kx value or depending on what is the nx value. Okay, so there's actually multiple solutions to this, or multiple behavior of the electron, right? In this case, the momentum of the electron is described by h bar k. Okay, that's the definition of momentum in a quantum mechanical sense, where h bar is the normalized Planck constant. I mentioned this before, h over 2 pi. Okay, so that's the momentum of your electron. So you see that it is totally different from classical physics, right? Classical physics momentum is mv, whereas in quantum mechanical particles, right, the momentum is h bar k, where k is like a wave vector. So if you try and compare these two, you can kind of see that, of course, there's some equivalence to this, and if you compare the terms, the velocity term is like the kx term, right? Because the h bar is a physical constant, m is like a mass, also like a constant. So the kx is like equivalent to the velocity. So loosely speaking, you can think of the wave vector as like a velocity component for the electron. Okay, kind of describe the velocity of the electron. And in terms of the energy, right, the solution for the energy, you find that it gives a solution of h bar kx square over 2m. Okay, where the energy of the electron actually depends on the wave vector. And if you look at the solution for wave vector kx, it is actually not a continuous value, right? Because here we say that this n here is an integer value, which means that the kx is also discrete. Okay, discrete. You can only take on specific values defined by n, which is an integer. So you cannot have a continuous value. Let's say 0.001 of k or 0.00002, 0.003. It doesn't go continuously. Okay, you only take on specific discrete values. Which means that the energy solution that we're finding here is also discrete in nature, right? Because if kx depends on nx, then it will also mean that the E depends on nx. So we take on specific discrete value. In fact, if you draw the energy, okay, versus k in this case, which is like the energy against momentum, because that's how I say that this k here, it's essentially like velocity, right? And there's an equivalence between that and velocity, and collectively you can think of that as like a momentum quantity. So if you do a plot of all the different possible n value and E, you actually get these points. Okay, and these points obviously will sit on a parabola. Okay, because similar to classical case, your energy against the momentum is also parabolic. Okay, so this is the kind of like the solution for an atom, which is not surprising, right? Because previously when we talk about solving the Schrödinger equation for atom, we see that the energy of your electron is actually discrete, which is in agreement with this, right? If you just draw just specifically the energy levels, okay, these are actually kind of like the discrete levels that you would expect, okay, for electron in an atom. Okay, so this discrete energy should not be surprising to you. Okay, but of course, if you plot it with respect to momentum or the k, then you will similarly observe this parabolic relation. Alright, so for the case of this electron around an atom, okay, qualitatively they have this parabolic relation between the energy and momentum. Okay, so that's the conclusion from this analysis. So for in fact, like a free particle, in the case of electron around an atom, it's sort of like a free particle, right? Because it's just bound to an atom, it's sort of free to move. You find that there's some equivalent to classical particle in the sense that the energy is discrete, and also the energy against the momentum relation is parabolic, like classical particle. Okay. Then the next question is, what about for electrons in a crystal? How would the energy against the momentum curve looks like? Okay, so to answer this question, we have to analyze in the case of electron in a crystal, what exactly is the setup. So for single atom, just now we mentioned that we can represent this potential energy profile of the electron as a well structure, right, to simplify the analysis because the values are constants. Okay. What about in the case of electrons in a crystal? So if you look at electron in a crystal as it's moving about in the crystal, you will see the nucleus of the various atoms, right, which is positively charged. And for each of our atom, it will have a certain potential energy profile. Okay, so here we basically show, so in this case, this will be nucleus of an atom, this is another nucleus, right? If you consider a one-dimensional case again, like the single atom, okay, let's say I have a crystal, right, with atom space at some distance apart. When you have an electron that's moving in this region, okay, we have an electron that is, let's say here, and it's moving, right? These electrons will experience this potential energy from this individual nucleus, right? And we know that for each of the nucleus, the relation is 1 over r. So at the respective position, you will get this 1 over r relation. Okay, but of course, it's in an environment where there's this nucleus that's arranged in a periodic manner. So the combined effect of the potential energy of this electron will be the sum of these individual potentials. Okay, so if you add all this up, then the potential energy that an electron will see when it's in a crystal will be this graph that you see at the bottom here, right? So if an electron is moving in this semiconductor, it actually would have this potential energy profile. Okay, so that's the idea now. And of course, in order to sort of solve for the energy against the momentum profile, right? For an electron in a crystal, we basically would need this potential energy profile to put into the Schrödinger equation, right? So theoretically, if you solve it, then you can find out what's the energy against the momentum relation for an atom in a crystal. Okay. So of course, you know, if you use this actual graph and put in the Schrödinger equation, you can do that, but the challenge is that because this is quite difficult to solve, right? It's a sum of many 1 or R curves. You put in the Schrödinger equation, it's quite complex to solve. Okay, so again, you know, we can adopt a similar approach to that of the single atom, right? Instead of using the actual potential profile, we can actually use the approximation, like what we did before. Okay, so right, we fit some approximate structure to this so that the values at different places is constant values. Okay, and if you do that and put in the Schrödinger equation, it's a lot easier to solve. Okay, so this approximation, it's you know, invented by or used by some scientists. So collectively, we refer to this as the Crony-Penny model. Okay, so it's kind of like an approximation to make it easier to solve in Schrödinger equation so that we can get analytical expression. If we use the actual 1 over R relations, right, you know, this actual curve, the blue one, then it's very hard to solve in the Schrödinger equation, and you have to use numerical method to solve for the solution. Okay, so this gives us a mean to get approximate analytical solution that allows you to see, you know, how it affects the band structure of the semiconductor. So anyway, without going into detail, right, of course we are not expecting you to be able to solve this. Here we are just requiring you to have an appreciation, okay, understand the process. So if you put this in the Schrödinger equation and solve it, then you get the solution for the wave vector kx as 2 pi n. Again, there's an n value there. Okay, so n is an integer over L of x. Okay, L of x here is the size of the crystal. Okay, so it's not the spacing of the well anymore, it's the actual size of the crystal. Alright? You find that it's different value. Okay, with the different n value, your spacing for k of x, right? Okay, the delta kx, the spacing of the delta k between consecutive k values is 2 pi over Lx. Okay, so this is actually an extremely small value because the Lx, okay, the Lx is the size of a crystal, right? So in reference to the atom, this Lx is very large. So which means that the delta kx is actually a very, very small value. So they're actually very closely spaced. Okay, to approximation that we can think of it as almost continuous. All right, and similar to the case of a single atom, okay, the momentum is defined as h bar kx, and this momentum here, specifically for electron in a crystal, we call this the crystal momentum. Okay, because in this case, right, this solution here is derived taking into account the influence from the different atoms in a crystal. Okay, so it's not like free space anymore, like the previous discussion. In this case, you actually have interaction with the different atoms that's been taken into account, right? Because that's what you put in to the Schrödinger equation, and the final solution actually has the effect of interaction with the atoms taken into account. Okay, so collectively we call this a crystal momentum, right? It's not the free space momentum, like in the case of classical mechanics. Okay, so right, so so in the case of this free electron or electron around an atom, right, we see that there's a parabolic relation, okay, between the energy and the momentum. What about the case of electron in a crystal? Okay, so if you solve this Schrödinger equation for electron in a crystal, right, other than getting the wave function and the kx value, the solution for energy against momentum actually looks something like this in this graph, figure 3.12. Okay, so again, don't worry about how you get to this solution, right? Just appreciate that if you saw a Schrödinger equation for electron and a crystal with these periodic atoms, okay, in other words, you put in the periodic potential energy, the approximate potential energy, this is the solution you get. Okay, this is actually the solution you get. You have actually this series of curves that is actually broken at certain parts in the energy direction, right? So like, for example, this part here, it's a gap. So this part here, actually, there's no energy states. Okay, then the other part is here, where again, there's no energy states. Okay, and the other parts, you have some energy states that electron can occupy. All right. So it turns out that the lowest two part, okay, this portion downwards, if you calculate how many states there are and how many electrons you have, you find that this part downwards, it's all fully occupied by electron at 0 Kelvin. Okay, the part above, it's actually all empty at 0 Kelvin. Okay, in fact, this part here, right, the lower part where that's all filled up with electron, this part is actually the valence band. And the upper part that is empty at 0 Kelvin is the conduction band. Okay, and the middle part where there's no states, that's the band gap. Okay, so this is actually the EG portion. But of course, take note that in this graph, we are plotting energy against the previous one that we showed two lines, right? And we say that this is kind of like EC, EV, and then we have a band gap, okay, EG. Okay, this is different from this graph here because the horizontal axis for this diagram is actually physical distance in the semiconductor, whereas the horizontal distance in this diagram is actually the wave vector, or like the velocity component of the electron. Okay, so there's a slight difference between these two, right? So be aware of this. Now it turns out that because the potential energy of the electron, okay, the potential energy of electron in the semiconductor is periodic. Okay, the solution here, the E against K graph, is also periodic. Okay, and what that means is that we can actually shift the graph by integer multiple of the periodicity. Okay, so that we don't have to consider a whole range of the K value. Okay, so instead of needing to consider the whole range, we can actually collapse this to a narrower range. Okay, to analyze the characteristics of the EK behavior. Okay, and the periodicity would mean that we can actually shift this curve, right, to the right hand side by we can shift it to here, which is kind of like this, and this one we can shift to this side. Okay, so it goes like that. So we effectively shift it by 2 pi over a, and the behavior would remain the same. Okay, so if we shift it, similarly, if we shift it by integer multiples of 2 pi over a, this guy can come to here, right? Okay, this guy can come to here, and this guy can come to here, which would kind of be like that. Okay, we just consider a narrower range. Okay, we just consider this very short range from minus pi over a to pi over a to analyze the behavior. Okay, we do not need to consider the whole thing. Okay, if you do that, hello? Can you still hear me?
Yes.
Yes, yes.
Yes, bro.
Yes, okay. Okay, great. Hello?
Yes.
Is it okay? Are you all following, or like the video sort of break somewhere? Still okay, you can hear me, right? Is there any part that is cut off?
I don't think so.
Is there any part that's cut off?
I don't think so.
Sorry?
I don't think so.
Okay, great. Okay, so I continue. Now, so if you... Okay, let me see. So someone mentioned that Anushka was trying to get in, but she got locked out. Is she in already, or is she in?
I used my friend's account to get in, but I'm still in the...
Okay. Oh, okay, right. Can you try and come in again? So if you use the official NTU account, then you will come in straight away, lah. You know, so it's best that you use the official NTU account to log in. Yeah, but if not, can you try and come in again, and I'll meet you?
Okay, sure.
Yeah. Okay. Yeah, so it'd be good if you all can log in using the NTU official email. Okay, if not, you know, I may overlook and may not be able to log in straight away. Okay, everything is good. Okay, let's continue now. So as I was saying, because of the periodic nature of you know, the potential energy and the crystal, right? Turns out that in this EK solution, we can actually shift the curve by integer multiples of 2 pi over a, and it doesn't change the behavior. Okay, so we can actually do that. So again, don't worry too much. Just appreciate. Okay, and if you do that, then you actually get this kind of relation, which describes the energy against the momentum of the electron in a crystal. Okay, so qualitatively, you can think of this as the kinetic energy of the electron versus the velocity of the electrons in the semiconductor. Okay, that's similar. And as I mentioned before, right, this part downwards is actually energy states that's filled up with electrons in the crystal. And this part here above is actually the empty states. Okay, so this refers to the conduction band, right, the EC part, right, and this part downwards is the EV part. Okay, and of course the separation here is the band gap. And in fact, if you look at this EK relation, of course, it's no longer a purely parabolic relation, right? It's kind of a funny parabola, especially near to this region, right? It's still about parabola, but as you go higher up, it sort of curves differently, right? It's no longer the nice parabola that you will see, but nevertheless, near to the band edges, right? It's approximately parabolic. Okay. So now this EK relation is an important sort of property because it describes the relation in terms of how the energy of the electron changes with momentum, okay, in the semiconductor crystal. And this EK relation is actually also direction dependent. Okay, it's direction dependent because if you think about it, the solution that we get is from putting in the potential energy, which depends on the spacing between the atoms, the nucleus of the atoms, right? If you go in a crystal in different direction, then the spacing will change, okay, and you expect the solution of the EK to also change. Okay, so in other words, it's actually a function of direction in a crystal as well. Okay. Okay, before we come to that, so we mentioned that the EK relation, right, the conduction band and the valence band, although it's not a pure parabola anymore, but approximately near to the edges, right, the EC and the EV. Okay, so we go back to this figure, right? I say that this is the EC, this is the EV. Near to this region, right, close to the band gap, is still approximately parabola, conduction and the valence band. Okay, so a lot of times we can approximate this EK relation as just parabolic. Okay, especially most cases the electron would be around the conduction band edge, right? Unless of course you accelerate the electrons to very high energy, right? Then they could go a lot higher up. But in most applications, you find that they will tend to stay around this region, which means that we can actually assume an approximate parabolic relation between the energy and momentum in the crystal. Okay, so that's a point that you can take note of, right? Okay, as I mentioned before, the EK relation is actually direction dependent, and so wherever we show the EK relation of a semiconductor, right? Okay, we don't just show the EK relation for one direction. Okay, instead, if you look at textbooks, okay, if they show you the EK relation, you typically will find the EK relation, comprising of different directions that's pieced together. Okay, for example, if you look at, gallium arsenide, okay, on the right hand side from the 0 value, you have the 100 direction, right? Remember the square bracket indicates crystal direction. On the left side, they piece together the 111 direction. Okay, and this is okay because if you look at the EK relation that we have just now, right, it's actually symmetrical about the vertical axis, which means that if I know one half of it, automatically I can derive the relation on the other half. Okay, so in the context of the K, right, K is kind of like a vector. So whether you go in a positive direction of that wave vector, or you go the opposite direction of the wave vector, the EK relation is the same, it's symmetrical. Okay, so as long as you know one direction, you can infer the other direction. So it's conventionally sort of common practice to just drop one side of the EK diagram for different directions, and we piece it together, right, to give us a sense of how the carrier will move when they move in the semiconductor in different directions. Okay, so we find that the EK diagram of semiconductor shown in textbooks actually will have multiple directions pieced together. Here we just show two directions, the 100 and the 111 direction. Okay, so that's kind of typically what is being shown for EK diagram. Now, so based on this EK diagram, right, we can actually define semiconductor into two different categories. Okay, so for those where the EK diagram has the minimum point in the conduction band being at the same K value as the maximum point in the valence band. Okay, if this maximum minimum in the conduction and valence band are the same K value, then we call this a direct band gap semiconductor. In the case where they occur at different K value, like this one that you see here in silicon, okay, silicon EK diagram is actually this. You find at the minimum point K value and the maximum point K value in the valence band and the conduction band, they are different K values. Okay, so for such a semiconductor, we call this an indirect band gap semiconductor. Okay, so there's a difference. Of course, the band gap is always between the lowest point in the conduction band and the highest point in the valence band. Okay, this separation here is called a band gap. All right. So what's the difference between these two types of semiconductor material, right? So if we look at the direct band gap semiconductor material, okay, in such a semiconductor material, if you have some electrons in the conduction band, okay, and some holes in the valence band, then for an electron in the conduction band to get down to the valence band, this actually can occur quite readily, because if you look at this, right, you think of this as like particles. Okay, for electrons to get down to the valence band, or if you think of interaction between particles, so in classical mechanics, if you think of interaction between particles, a few conservation rule holes, right? The first, of course, is conservation of energy. When you have two interacting particles, let's say two particles colliding, okay, before impact and after impact, we can apply the conservation of energy, right? You expect energy to be conserved. The other thing that you expect to be conserved for elastic collision, particularly, is that the momentum is conserved as well. Okay, so in the case of semiconductor like this, right? If you have electrons in the conduction band, right? That's you can think of it like before impact to electron coming back down to the valence band, kind of like after impact. You will expect the conservation of energy and conservation of momentum to be satisfied, right? In order for this process to occur. So for conservation energy, it's not a difficult thing to do, right? Where electrons go from conduction band to valence band, there's a change in energy, right? There's a loss in energy. This loss in energy, the energy must go somewhere, okay? So when an electron comes from the conduction band to the valence band, this energy can be given off in a form of light, okay? So it can emit a photon, in other words. Okay, so that can be conserved by emitting a photon. Now what about momentum? Okay, so if we think of momentum, before it carry out that process, the momentum in this case is at k equals 0, right? After the transition, when it comes down to the valence band, okay, to this point here, the k value is the same, which means that the k value actually don't change. What is k value? K value is like a momentum quantity, right? So for direct bandgap semiconductor, coming from conduction to valence band, you find that the momentum doesn't change, which means that it is automatically conserved. And imply that this transition can occur readily. Okay, it can occur with a high probability. Okay, so we find that in direct bandgap semiconductor, this recombination process can occur readily to emit a photon. Okay, so in other words, a direct bandgap semiconductor can emit light quite readily. Okay, that's the property of a direct bandgap semiconductor. Now, what about indirect bandgap semiconductor? Can it do the same? Okay, so if we look at this, right, if you have an electron in the conduction band and it tries to get down to the valence band, okay, again, this transition, there's a change in energy, that energy must go somewhere, right? So this again can be emitted as a photon, okay, so that you can satisfy the conservation energy. Now, what about the momentum? If you look at the momentum, initial electron here has this k value, right? Some momentum value. When it goes to the valence band edge, if it's different, it means that the momentum changes. And if you want to conserve this momentum, right? In other words, the momentum conserve means that it doesn't change, right? You must involve some other process that can help to balance this change in momentum, right? You need to have involvement of a process that helps to balance off this change in momentum, right? This momentum that is now different. So, and this then makes it a lot harder for electron to get back down to the valence band and emit a photon. Okay, of course, theoretically it is possible, right? One possible process that you could interact with to give it a countering momentum, right? So that it cancel off and you have a net change of 0 for momentum, so that the momentum is conserved, is by interacting with vibrating atoms in the crystal. Okay, because these vibrating atoms also have some momentum, right? So for example, if an electron is moving and it's trying to recombine, if it can find momentum that exactly matches this change but opposite sign, so that you cancel it off from the vibrating atoms, then theoretically you can conserve momentum and go down to the valence band. Okay, theoretically. But in order to find this exact momentum for it to match, it's a lot harder. Okay, it's a lot harder because there's this varying range of momentum. So instead, this process is harder. Instead, what is more preferred for electron in such a material is that they tend to go back down to the valence band through what we call defect levels in the bandgap. So it turns out that in practical semiconductor, you actually get defect levels in the bandgap, okay, because of imperfection in the crystal. So we have a pure, nice crystal with no defects, okay, in the crystal, then the band diagram will look like this, right? But you have imperfection, like for example, some location an atom is missing in the lattice, or there's an extra atom in between lattice. Okay, this will actually introduce additional energy levels in the band gap, okay, which we call defects. Okay, so it turns out that for such a material, instead of going directly right from here to here, which would not occur so readily, in other words, probability is low. But instead, if you go through the defect levels, that means you go to some defect level and transit down, okay, to the valence band. Then this is actually easier, and in doing so, right, it loses the energy as heat to the crystal. Okay, so this is actually higher probability, right? This transition is higher probability, and as a result, you find that for indirect bandgap semiconductor, it's harder for electrons to go directly to the valence band and emit a photon, but instead they tend to go back down through these defect levels and emit the energy as heat. Okay, so you don't get light from such material so easily. Okay, so of course I'm not saying that in direct bandgap semiconductor there's no defect. Okay, similarly in direct bandgap semiconductor you also have defect levels, and in fact it's a competing process, right? So you can have electron going through these defect levels now versus direct, where they give off a photon. Okay, so what we're saying here is that in the case of direct bandgap, this direct recombination to give a photon, the probability is higher compared to indirect bandgap, where this process of emitting a photon by directly going from conduction to valence band is harder to achieve. Okay, so that's the difference between a direct bandgap and indirect bandgap semiconductor. And in fact, in light emitting applications, right, like for example in LEDs, okay, typically we use direct bandgap semiconductor for light emitting purposes. Okay, like semiconductor laser, semiconductor LEDs, we use direct bandgap semiconductor. So things like silicon, we don't use it for light emitting because they're not efficient. A lot of it will be wasted as heat. So instead we use silicon for electronics application instead. Okay, so we need to appreciate the difference between a direct bandgap and an indirect bandgap semiconductor. Right?
Professor?
Yep.
When you say defect in the semiconductor, do you mean the missing atoms, like in this case, maybe missing silicon atoms in the lattice? Or
yes, in the lattice. Impurity also, as well. So all this will introduce defects into the semiconductor.
Okay, thank you.
Yeah. Okay. Right. So another quantity that is important for us to define is what we call the effective mass of electrons in a crystal. Okay, so if you think about it, the electron now in a crystal is actually not in a free environment where it's free space, right? There's no influence. In the case of electron in a semiconductor, is moving in an environment where there is influence from the nucleus of the atoms, right? The nucleus of the atom exerts some force on it. So when you want to describe the movement of an electron in a crystal, okay, if you consider all the force that's applied by the electron, there is essentially basically two components we can think about. So suppose I have a semiconductor, right, and let's say I apply some voltage across it, and this will set out electric field, right? Okay, the electric field will exert a force on the electron. So the electron here will obviously experience this electric force, which is due to some external source. We denote this as F external, EXT, right? And internally, because it's also passing through a lot of atoms, okay, which have nucleus that will exert some force on it, you will actually also experience all internal forces, right? Okay, so you have this multiple internal forces. Okay, so collectively here we just write a single term, F internal. So really there's a lot of different internal forces that's experiencing, and the total force that the electron will experience is the sum of these two, right? More correctly, the vectorial sum of these two components. Okay. So, and of course, if you apply Newton's law, then it's equal to ma, Newton's law, right? And in a classical way, we can define it as mass times acceleration. So that's the way to kind of describe the movement of the electron, right? But if you use this kind of representation, then it's actually quite tedious, because in addition to the external force that is applied, you find that you also have to take into consideration this internal force, which is troublesome, because as the electron is moving, the internal force it experienced from the whole crystal itself will be changing, right? Because you move away from one atom, it goes towards another atom, so that force component will change. So this component here, other than being varying, is also quite difficult to determine. Okay, so then the question is there an easier way that we can take into account this internal force, such that, for example, if we can embed it into, say, the mass quantity, right? Embed the effect into the mass quantity, and leaving just the external force that we need to worry about, then we can write it as external force equals to a product of some representative mass value with the acceleration. Okay, so if we can do that, then it will simplify the analysis a lot. Then it becomes like a classical analysis of a particle. Okay, so it turns out that in the case of electron and semiconductor, we can exactly do this. Okay, by the way, this sort of representative mass quantity is called the effective mass. Okay, in other words, we would have taken into account the internal interaction. And in the case of electron in semiconductor, right, turns out that we can actually do that. So if you consider the case of this free electron particle, right? Okay, we have a solution of energy equals to h bar k holding square over 2m. It's a parabolic relation, right? If you do a derivative of this respect to k, that means you differentiate this respect to k, right? Then you have dE dk equals to h bar square k over m. Okay, differentiate k square, you get 2k. Okay, the 2 and 2 cancel, you get k over m. So first derivative, you get this quantity here. And in fact, this first derivative is related to momentum. Okay, where momentum is h bar k, you put this into the equation, you find that we can find some relation for the velocity component, which is 1 over h bar and the derivative of the energy against momentum. Okay, so in other words, the first derivative of the EK diagram gives you the velocity component. If you differentiate this again, right, then the k will disappear, right, because if you differentiate k again, k becomes 1. The second derivative of the EK diagram actually gives us just h bar square over m. Okay, so we rearrange this and write m in terms of the other quantity, we actually get this mass that is derived from the second derivative of the EK diagram. Okay, so the mass sort of behavior, right, can actually be derived from the EK diagram. So in other words, if you have the EK diagram, you take second derivative, right, and you take the reciprocal of that, multiply by h bar square, you get the sort of mass quantity of the electron in a crystal. So in the case of electron in a semiconductor, remember we say that the EK diagram is actually approximately parabolic at the conduction band edge and the valence band edge. So if it's parabolic, we can actually use that derivative definition that we mentioned earlier, right? Because we derive it based on the assumption that the EK relation is parabolic. Okay, so if you assume that that relation derived earlier is applicable because this is approximately parabolic, then we can actually write down the effective mass as the reciprocal of the derivative of the second derivative of the EK diagram. So in other words, this second derivative of EK diagram actually gives us some effective mass quantity for the electron. Okay, this second derivative basically refers to the curvature of the curve of the EK diagram. Right, this is math, right? If you find second derivative, it's actually referring to the curvature, how fast the gradient is changing. All right, and similarly for the case of holes, which is a positive charge, right? So the effective mass will be positive. If you apply this to the EK diagram, if you do a second derivative here, your value is negative. But if you apply it to a hole, it reverses the sign, and we get the positive quantity of that being the effective mass of holes. Okay, and the good thing here is that the EK diagram is actually a relation that has taken into account the internal interaction with the force, right? Because remember, when we solve for this, we use the potential energy of the atoms interacting with the electron. Okay, so in other words, the internal effects is actually taken into account already in the EK diagram. So if you find the mass from the EK diagram, you essentially get an effective mass quantity. Okay, so so this part here can be used to describe the motion of the electron or the holes in the semiconductor. And because it's parabolic, in fact, we can use this Newtonian physics to analyze. Because it's parabolic, then it's identical to Newtonian mechanics. So a lot of times you can just use Newtonian mechanics with the effective mass to describe how the electron move in the semiconductor. Okay, under this limiting case, where if it's near to the conduction band edge or the valence band edge. So this actually helps to simplify the analysis. All right. Okay. Okay. Yep.
Sorry. Could I clarify? This equation works for both the hole and the electron, right?
Yes. The only thing is that for holes, if you do the second derivative, you need to take the magnitude of it, because if you just take the second derivative, you actually get a negative sign, which is not surprising because that's the negative sign is for the electron. If it's for a hole, it's a positive charge, the sign will inverse.
Oh, I see. Thank you.
Yeah. Okay. Okay. So yeah.
Does this mean that the whole effective mass is always positive?
Yes. So the negative sign would mean it moves in the opposite direction, right? Okay. So let's maybe take a 10 minutes break, and let's come back at 5:30, and we can continue with the rest of the discussion. All right. Let's take a 10-minute break.
Then for the conduction band, would the effective mass be the same? Will have the same sign?
The conduction band.
Yeah.
Same sign as what?
Like, would it still be like negative for the electron and positive for the electron hole for the conduction band?
For the mass?
Yeah, the effective mass.
No, the effective mass is positive. The effective mass is positive because if you take the second derivative of a minimum parabolic curve, right, you will get a positive value, right? Minimum point, if you do a second derivative, you get a positive value, right? If it's negative, it's a maximum point. So in the case of conduction band, if you do a second derivative, you find that the value that you get will be positive. Okay, let's do a 10 minutes break. You can come back at 5:30, then I'll continue the rest from 5:30 onwards.
doping of semiconductors.
Okay, let's continue. Okay, the next part I'm going to just briefly talk about the doping in semiconductors. As I mentioned before, as a semiconductor crystal in its pure form, its use is actually a little bit limited. Okay, because to put it into practical use, you need to be able to kind of vary the number of free carriers in a semiconductor. Okay, a pure semiconductor does not have so many free carriers, right? Because you put it at room temperature, you find that you do get some electron pairs being generated, but the number is typically small. So in order for a semiconductor to be useful, you have to be able to change these numbers of electrons and holes in the semiconductor. And we kind of do that by doping the semiconductor, okay, with what we call impurity atoms, okay, impurity dopants into the semiconductor. All right. So now if you look at, in the case of pure semiconductor, we say that the carriers come from electron pair generation due to essentially thermal effects. The electrons get up to the conduction band, becoming a free carrier, and this creates a vacancy in the covalent bonding, which gives you the corresponding holes. Okay, and these two guys can sort of move in the conduction and valence band respectively to carry the current. Okay, so in a pure semiconductor, this stable number of electrons and holes, the numbers per unit volume, right? It's denoted as intrinsic concentration. Okay, so we denote them as Ni for electron intrinsic concentration. So this actually is a measure of how many free electrons there are per unit volume in the semiconductor. So similarly, in the case of holes, the intrinsic concentration of the holes is Pi, which in a pure semiconductor, this two number must be the same because they are always created in pairs. Okay, and you would expect this Ni and Pi to increase with temperature, which is intuitive, right? If you increase the temperature, there's more thermal energy, there will be more electron that can transit to the conduction band, becoming free to move. So you expect the concentration of free electrons and holes to increase when temperature goes up. So bear in mind that when we talk about the physical form, right? Electron going from valence to conduction band corresponds to electron breaking off the covalent bonding, becoming free to move, leaving behind a vacancy that can move through electrons breaking the covalent bond from neighboring sites. Okay, so when it breaks and takes this place, the vacancy can actually transfer to other location, and it appears like it's moving in the crystal. So to sort of control the number of these electrons and holes separately, without depending on temperature, right? We can do that by putting in impurity atoms. Okay, so we're going to talk about how we can actually achieve that by putting in the different types of impurity atoms. So this kind of material that has impurity atoms added to vary the electron and hole concentration are called extrinsic semiconductor material. Okay, so they are not pure anymore. So there are actually two types of impurity atoms that we can put into the semiconductor crystal. One of the type is what we call the donor impurity atoms, and this typically comes from group 5 of the periodic table in silicon. Okay, so the elements that have 5 valence electrons are typically put into a silicon crystal to create donor impurity atoms. All right, so this could be things like phosphorus, arsenic, or antimony. Okay, so we're going to sort of review how this actually helps to introduce additional carriers into the semiconductor. Now, when we say we put doping in a semiconductor, essentially what we do is the process would remove a silicon atom and replace it with the dopant atom. So in this case, let's say we use a phosphorus atom to dope the semiconductor. Okay, so the process to dope it would effectively take out an electron, and then it puts in this phosphorus atom into the lattice site. Now, if you look at the phosphorus atom, right, it actually have 5 valence electrons, and in having this phosphorus atom in the crystal, 4 of the valence electrons will be used to complete the bonding with the neighboring silicon atoms, right? There's 4 that's required to bond with the neighboring silicon atoms. And this 5th one actually is then loosely bound to the phosphorus atom. Okay, so graphically, if you look at the Venn diagram, okay, this 5th electron corresponds to the electron that sits in an extra level just below the conduction band edge. Okay, the energy of this 5th electron that is loosely bound will have an energy that is slightly below the conduction band edge. Okay, and it sits there at 0 Kelvin. Okay, so that when there's no thermal energy, this 5th electron just sticks to the phosphorus atom site. Okay, and that corresponds to this electron at the this level here called the donor level. Okay, so in this diagram, you know, we actually draw multiple electrons there, and this is to illustrate essentially multiple phosphorus atom, right, in the crystal. So if you have a semiconductor crystal like this, right, each phosphorus atom will have one 5th electron that's loosely bound. Okay, so each of it will correspond to one of this electron, okay, that we draw in the Venn diagram. So at 0 Kelvin, everybody sits there. All right. Now, when you bring the temperature of this semiconductor up, okay, when there's now thermal energy, you find that this 5th electron, because it's loosely bound, right, it's quite close to the conduction band, you only need a little bit of thermal energy, and this will actually allow this 5th electron to break free. So in the Venn diagram, it corresponds to electrons sitting in the donor level going up into the conduction band. Because once it's in the conduction band, it's actually free to move. All right. So in doing that, you find that the phosphorus atom that it initially belongs to now loses one electron, and that makes the phosphorus atom positively charged. Okay, it becomes ionized. Okay, so when it's positively charged, we say that it becomes ionized, and this corresponds to fixed positive charge in that lattice position. So notice the difference between this and a hole, right? A hole corresponds to a vacancy between the silicon-silicon bond, and this vacancy can actually move by having another electron from a neighboring silicon-silicon bond breaking off to replace that vacancy, so that the vacancy shifts to a different lattice position, right? In the case of this ionized phosphorus atom, okay, this phosphorus atom is fixed in location because it's covalently bond to the neighboring silicon atoms. It actually cannot physically move. Okay, so in other words, this ionized phosphorus atom is actually in a fixed position which doesn't move. Okay, so this positive charge actually will not conduct current. All right, so you need to be able to distinguish this from a hole. Hole can move. This ionized dopant, it doesn't move. It sticks in a position in the crystal lattice. So in the band diagram, you see that in having the electron going from donor level into the conduction band, it actually does not create a corresponding hole, right? On the other hand, if you have a band-to-band transition, okay, then you get a hole that is produced. Okay, so in this semiconductor with dopings, there's actually now two contribution source for electron. One from the intrinsic property of the semiconductor, which is the band-to-band generation, right, which gives you an electron plus a hole. And the other source is from the ionization of the dopant, which just gives you the electron. Okay, it doesn't give you a corresponding holes, but instead it causes the dopant atoms to be ionized, which is fixed in position. It doesn't move. Okay, and of course, if you keep increasing the temperature up to a certain temperature where it's sufficiently high, you will expect all the electrons in the donor level to go into the conduction band. Okay, so in this case, we say that the semiconductor is fully ionized. Okay, it's fully ionized. Okay, and this is this condition here, right? All the electrons are promoted to the conduction band for the donor level, and we say that all the impurity atoms are fully ionized. Okay, and if we denote the total number of electrons in the conduction band as N naught, so we use a different notation for intrinsic, right? Intrinsic, we use Ni. So for general semiconductor with doping, we just use N naught to indicate that it's an equilibrium condition electron concentration. And correspondingly, if we denote the whole number as P naught in the valence band, and let's say the number of dopants in the semiconductor is ND, right? So we dope the semiconductor uniformly with ND number of phosphorus atoms, then we can actually write a relation between N naught, P naught, and ND. Okay, so ND will correspond to this numbers of donor atoms there. Okay, and if you look at this graphically, we can see that the total number of electrons, as we mentioned before, comes from two sources, right? So the N naught is made up of contribution from ND, right? Because each phosphorus atom gives rise to one electron, right? One donor electron. So if there's ND number of phosphorus atom per unit volume, then you expect ND number of electrons per unit volume. Okay, so that is one source of electron, right? Your ND there. And of course, the other source of electron is due to the band-to-band transition, okay, which is this group here. And we can tell the number from the number of holes that is present, which in this case is just purely due to band-to-band P naught. So if you have P naught number of holes, you expect P naught number of electrons that is also contributed to the conduction band due to this band-to-band transition. Okay, so we add the P naught there. So we have N naught equals to ND plus P naught. Okay, we call this the charge neutrality equation. Okay, so this expression here that we see, it's actually called the charge. Okay, neutrality equation. Okay, charge neutrality, because if you look at it from the point of view of conservation of charge, okay, you can also get this equation, right? If you think about it, the total number of negative charge, which are just the electrons, right? You have N naught number of negative charges must be equal to total number of positive charges. Okay, so positive charges will be made up of holes, right? That's one source of positive charge. And the other source is actually the ionized dopants, which is actually ND as well. Okay, so the ND here can also mean the total number of positive charge. Okay, if you add up ND with P naught, that gives you the total number of positive charge must be equal to the total number of negative charge, right? So the N naught here. So this equation is also like a conservation of charge equation. That's why we call this a charge neutrality equation. Okay, so do keep this equation in mind, because later on we're going to use this equation to do some analysis and work out the concentration of N naught, P naught, and other quantities in the semiconductor. Okay. So at this temperature where you have all the donor impurity atoms ionizing, okay, we call this impurity saturation condition. All right, and so in this case, by the way, we call this donor electrons. Okay, those that come from the donor impurity atoms. All right. So, looking at the charge neutrality equation of N naught. Okay, if we look at the charge neutrality equation, N naught equals to ND plus P naught. Because of this extra N naught quantity there, right, you can obviously see that the N naught is always greater than P naught. Okay, so in other words, there's more electrons than holes in such a semiconductor material. So we call this type of semiconductor material the N-type semiconductor. Okay, because there's more electrons than holes. And in this kind of semiconductor material, the electrons are called the majority carriers because they are larger in number, and the holes are known as the minority carriers because they are smaller in numbers, right? Okay, so these are terminologies that you need to take note of. N-type semiconductor, majority carriers are electrons, minority carriers are the holes because of difference in the number, right? So Okay, let's do an example to see how we can actually estimate the donor binding energy for gallium arsenide by considering the hydrogen sort of atom case. Okay, so in the case of this gallium arsenide, okay, suppose I have a gallium arsenide and you have donor atoms in gallium arsenide crystal. Okay, so the donor atoms will have this fifth electron similar to silicon that's loosely bound. So the question we're asking here, right, effectively is, what is this energy of this fifth electron that is bound to the impurity atoms? Okay, that's called the donor binding energy. So we can actually calculate this or estimate this by first considering the hydrogen atom, which have this similar configuration, right? In the case of hydrogen atom, we have an electron and a nucleus, okay, that is bounded. And from our discussion in lecture 1, right, or lecture 2, I can't remember. Okay, we see that the energy of this electron around some nucleus, okay, it's given by minus 13.6 over n square if you substitute in the various quantity, right? And if you look at the equation of the energy, right, there is a few terms, okay, which is the m naught. Okay, the m naught here basically refers to the rest mass of the electron. So in the case of electron in a hydrogen atom, we can just use the rest mass of electron. Okay, so we can actually apply this sort of model to the donor impurity atoms in gallium arsenide, because the fifth electron is, it's quite similar to a hydrogen atom, where it's kind of like one electron bound to the nucleus, right? So if we apply this equation to the donor atoms in a gallium arsenide crystal, then the mass of this electron will no longer be just the rest mass. Because remember now, if you have this impurity atom in a crystal, right, the electron now is in a crystal, which means that the mass is no longer a rest mass, it's actually a effective mass, right? It's experiencing interaction from atoms in a crystal. Okay, so if you want to use this equation in the context of a donor atom in a gallium arsenide crystal, we can modify this m naught to effective mass. Okay, there are quantity that we need to modify. You're going to apply this equation to the donor impurity atom in gallium arsenide. It's actually this epsilon naught value, which in the case of electron in an atom, it's permittivity of free space, right? There's nothing around it. But in the case of impurity atoms in a gallium arsenide, the surrounding now is the crystal itself. So we have to use for the epsilon naught in its place, right? Replace it with the permittivity of gallium arsenide, because the surrounding is a gallium arsenide material. So if you do that modification, you can actually use the same equation to estimate the energy of this fifth electron of the impurity atom in gallium arsenide. Okay, so that's the approach. So the effective mass of gallium arsenide, okay, this quantity is actually something that you can find in textbooks and reference material. So anyway, if you do find it, you find the effective mass of electron in gallium arsenide is 0.067 of the rest mass. Okay, that's the quantity that we should be using. And the permittivity of gallium arsenide is 13.2 of the permittivity of free space. Okay, so there's some material now, the permittivity will be higher. All right. And if you modify the energy equation of hydrogen, then it becomes if you substitute in all the values, right, it becomes minus 0.0052 over n square. Okay, so what this means is that the energy of this fifth electron of the donor impurity atoms in the crystal is given by this expression where n is positive integers. All right. Okay, so if you were to actually sketch the energy of this fifth electron, right, starting from the lowest value n equal to 1, okay, is minus 0.0052 eV. Okay, so that's n equal to 1, for example. If you substitute n equal to 2, then it's a slightly less negative number, so it's another value here, right, n equal to 2, n equal to 3. And if we keep going, right, then you will reach n equals to infinity, which will give you energy of 0. Okay, so in the case where this fifth electron is in the impurity atoms in the crystal lattice, generally you will sit at the donor level. Okay, so this lowest level here is in fact your donor level ED. So for it to become free, in other words, it has to go all the way up to n equal to infinity, right? This corresponds to the free energy part, which is like the conduction band H, right? Free energy portion, right? When it becomes free, then this level here basically is your EC, if you like. Okay, so the binding energy basically is the energy for electron to break free, right, from the bonding in the crystal. So in this case, the binding energy will be the difference between these two, right? If you give it this amount of energy, right? Okay, we give it this amount of energy between EC and ED, then the fifth electron can break free from the impurity atoms. Okay, so this is the binding energy, and this works out to just 0.0052 eV, which is actually very, very small. Okay, in other words, okay, this separation, right? If you draw in the context of the Venn diagram, for example, okay, in the case of gallium arsenide, the gap between EC and EV is actually, the band gap is actually 1.02 EV, right? So if the donor level is only 0.0052 EV from the conduction band edge, then you expect this donor level to be pretty close to the conduction band edge. Okay, this separation here is just 0.0052 of an EV. Okay, that's the binding energy. It's very, very small. So if you have a little bit of thermal energy, right, you expect the fifth electrons to be ionized quite easily. Okay, so you actually get into the conduction band very quickly. Okay, so the binding energy is very small. It's very close to the conduction band edge. So this calculation is just to give you appreciation of how close is the donor level to the conduction band edge. Okay, in fact, it's generally so close that at room temperature, all the donor electrons will be promoted to the conduction band edge. Okay, they become free to move. Alright? Okay, that's what we're trying to say here. Okay, so okay, so that's for the donor impurity atoms. Okay, so the name donor is used also because the impurity atoms donate electrons, right? It donate electron to the conduction band. That's why we call it donor impurity atoms. What about the other category here? The one that we talk about, right? Where the other type is actually using group 3 elements from the periodic table, and in this case, this kind of element is called acceptor impurity atoms. Okay, the reason why we use acceptor will become clear after we discuss how it introduces extra carriers into the semiconductor. Okay, so going by the same approach, right? If you replace or if you dope the semiconductor with acceptor impurity atoms, essentially what we do is we take out the host atom, in this case silicon, and we put in the acceptor impurity atom. So one such impurity that we could use is boron. Okay, so we put in a boron atom, which is group 3 in the periodic table. It has 3 valence electrons, and turns out that you bond with only 3 of the neighboring silicon atoms, and there'll be one that doesn't have a complete bond. Okay, it's actually a dangling bond. So this incomplete bond actually will have an energy level that is just above the valence band edge. So the energy of this incomplete bond is called the acceptor energy level, right? And this basically provide a state that electron from the valence band can go up to. Okay, so if you put this semiconductor at non-zero Kelvin temperature, so this in this case is 0 Kelvin. So you put it in temperature that's above 0 Kelvin, then what you find is that if you look at band diagram, right, your electron in the valence band would want to go up to the acceptor level. Okay, because if you think about it, right, comparing between the next level they can go to, would it prefer to go to the conduction band or the acceptor level? Obviously, it will prefer more to go to the acceptor level, right? You can do that easily with a small amount of energy, compared to if you go to conduction band, it needs a larger energy. So naturally, you expect this transition to occur more readily. Okay, so in having electron going up to the acceptor level, it will basically leave behind a hole in the valence band which can move in the crystal. So physically, what happens is that for this incomplete bond between the silicon and the boron, you can have electrons from a neighboring silicon-silicon bond, which will sit in the valence band, right? When this guy break off and they complete the bond between the silicon and the boron, it leaves behind a hole. Okay, and in completing this bond between the silicon and the boron now have one more electron than it has its neutral. Okay, so that actually causes the boron atom to be ionized. So the boron atom actually takes on a negative charge. So unlike electron, this boron atom is fixed in the lattice position, so it actually cannot move to conduct current. Okay, so this boron atom, like a phosphorus atom that we talk about in N-type semiconductor, they are fixed in position. They cannot move. Okay, although they have a charge, they cannot move. Okay, so this corresponds to a location in the crystal that is negatively charged, which does not move, right? And in this case, you should notice that you only get a hole that is created. You actually don't get the corresponding electron that is introduced in the conduction band. And if you denote the similarly for the N-type semiconductor, right, the number of holes in the valence band per unit volume is P naught, and the number of electrons in the conduction band as N naught, and the doping of the impurity atoms as Na to indicate acceptor impurity dopings, then we can similarly write down a charge neutrality equation, right, where we say that the number of holes, okay, in this case the number of holes is increased now, comes from two sources. One is from the acceptor doping, right, where each acceptor would give rise to one hole. Okay, so that's one source, plus the intrinsic band-to-band generation, right? This gives you one electron a hole each. If you have n number of electrons, it means that you have n number of holes that will be created based on this band-to-band transition. Okay, so if you add that to Na, it tells you how many holes there are in total. Okay. So the carriers are switched, right? In the case of N-type semiconductor, is N naught equals to, because N naught is the majority carrier, right, for N-type. Okay, for N-type, your N naught is equals to Nd plus P naught. Okay, whereas in the case of this case, where we put acceptor dopings, P naught is now the larger number carrier. Okay, so P naught is now on the left hand side. Alright, so there's a slight difference between these two. So similarly, if you have all the boron atoms ionizing, then we call this impurity saturation, right, where it's all ionized. Okay, and the source of the holes comes from two parts, right, from the impurity atoms and the band-to-band transitions. Okay, so being the larger number now for the holes compared to the electrons, we call the holes the majority carrier in this case, and the electron now is a minority carrier. So such a material is known as a p-type semiconductor material. Okay, so so that's the difference between the n-type semiconductor and the p-type semiconductor. So this basically refers to semiconductor that has doping, giving them more electrons for n-type or more holes for p-type semiconductor. Okay, the other thing like I would like to just quickly discuss is how the carrier concentration varies with temperature. Okay, so here we consider the case of n-type semiconductor, and in the case of n-type semiconductor, obviously we know that the dopants will be giving electrons. Okay, electrons is the majority carrier concentration. If you plot the graph of the majority carrier concentration with respect to temperature, then this is the kind of graph that you expect to see. Okay, and this graph actually have three regions. You have a region where the majority carrier concentration is slowly increasing, right? So in the case of silicon, that occurs up to about 150 Kelvin in temperature, right, this point here. And after which, you notice that the majority carrier concentration actually stabilizes to some constant value. Okay, we call this the extrinsic region. Beyond a certain temperature of 450 Kelvin for silicon, you notice that the electron concentration starts to increase again. Okay, we call this the intrinsic region. All right. So we're gonna try and understand what are specifically these different regions and why they behave like that. All right. So starting from the left hand side of the graph, okay, where you have 0 Kelvin, okay, there is no thermal energy. So if you look at the Venn diagram, you expect all the donor atoms, okay, donor impurity atoms, 5th electron to sit in the donor level. Okay, no thermal energy, everybody sits at the lowest energy level possible. And of course, all the electrons in the semiconductor would sit in the valence band for the silicon-silicon bond. Okay, so you don't expect to find any electrons in the conduction band, and that's why the electron density is 0, right? You don't see free carriers roaming around in the semiconductor. Now, what happens when you start to provide thermal energy to the semiconductor by raising the temperature? When you do that, right, you find that some of the electrons in the donor level starts to be able to gain enough energy to get into the conduction band. Okay, at the same time, you may also have some band-to-band transition occurring. But of course, in comparison, you expect this band-to-band transition to be very small in numbers. Okay, because the gap is larger, right? The barrier is larger, so it's harder for electrons to transit from valence to conduction band. As opposed to those in the donor level, which it has a smaller gap, so the barrier is a lot smaller, so it's easier for them to get up to the conduction band. All right. Okay, so you start to have electrons being present in the conduction band, and here we can write down a charge neutrality equation again, right? Except that this is a partially ionized case, so we write it as N0 equals to ND plus to only specify the ionized ones. Okay, so the ionized ones would contribute to electrons. Okay, those that haven't ionized, the electrons are still in the donor level. Okay, so we write it as ND plus, and obviously the ND plus would be less than ND, right? Because in this particular scenario, not all the donor atoms has ionized. Okay, and of course the other source is the P0, the band-to-band transition. Okay, so the carrier concentration actually will increase. If you increase the temperature, then you get more and more electron going from donor to conduction band, and the overall electron number will increase as you increase the temperature. That's why you get this increase in the electron concentration in the initial temperature from 0 to 150 Kelvin. So we call this a freeze-out region, okay, because it's like electrons in the donor level slowly freezing out, right, from its initial position. Now, when you go above 150 Kelvin, you find that there is sufficient thermal energy to ionize all the donor atoms. So all electrons in the donor level would have gone into the conduction band, okay, and they contribute to the majority of the concentration, okay. And although as you continue to increase the temperature, the band-to-band transition would increase the electron hole pair, this number would not be large. Okay, this is actually still a very small number. And if you look at the charge neutrality equation, right, although the N0 is made out of impurity atoms plus the band-to-band, this band-to-band number is typically very small. Okay, it's very, very small. So much so that it's approximately negligible compared to ND. So if you throw it away, because it's so small, right, it doesn't make sense to consider it. You find that the N0 is approximately equal to the donor doping. Okay, and that's precisely why in this region here, you find that the concentration of electrons is approximately flat. Okay, strictly speaking, if you zoom in, you'll see it increasing a little bit. Okay, but in a broader scale, it's approximately 0. It doesn't increase very much. Okay, so it's approximately a constant. Okay, that's called the extrinsic region because the concentration of carrier is largely dependent on the impurity atoms. Right, it's behaving like a undoped material. Okay, so we call this the extrinsic region. And in fact, in a lot of the application, right, in electronics, this is the region generally we keep the semiconductor in, because when you make a semiconductor device, okay, you want the concentration in the different parts of the device to be well defined. Okay, in other words, if the temperature fluctuates a little bit, you don't want that concentration to change. Because if the concentration changes drastically, then the behavior of the electronic device would also change. Okay, then that's not desirable because you want the behavior of the device to be predictable. Okay, like for example, if you have a computer, right, and your microprocessor have a lot of semiconductor material with dopings to make the device to make into that chip. If your temperature of your microprocessor in the computer actually increases drastically, if you don't cool it, you let it increase, right, to a stage where it changes the concentration in different parts of the semiconductor dopings, then you find that the chip will fail. It will not work as initially designed, right? For those who play computer, you know that the cooling of the microprocessor chip is important. If you don't cool it and it heats out too much, right, it will change the characteristics and the behavior of the microprocessor so much so that it doesn't work anymore, then your computer will hang. Okay, so in practical application, most times we keep the temperature of semiconductor within some well-defined temperature range where the doping or the free carrier concentration do not change with temperature. Okay, so that's the extrinsic region. If it changes, then it's a problem, right? Okay, so that's the extrinsic region. Now, why does the electron density actually continue to increase if you go beyond a certain temperature, in this case 450 Kelvin? Okay, you find that when you go beyond a certain temperature of 450 Kelvin for silicon, different materials will have different temperature when it happens. You will notice that this band-to-band transition, okay, becomes quite easy to occur, right? You get a lot of band-to-band transition. So much so that this band-to-band transition number, right, this number of electrons that's from band-to-band transition starts to overwhelm, it becomes the dominating number. Okay, so if you look at your charge neutrality equation, in the extrinsic region, of course, this ND is the dominant component. But when the temperature goes too high, right, then it turns out that the P naught will increase significantly such that the N naught can become negligible. Okay, and the N naught and the P naught now becomes approximately the same, which is this portion of the graph. Okay, it becomes so large that the N naught and P naught becomes the same, and this becomes like a pure semiconductor again, right? Because if you look at pure semiconductor, the number of electrons and the number of holes are the same. Okay, and this actually would not be the regular N-type, P-type anymore, right? It sort of revert back to a pure semiconductor behavior. Okay, and this is generally not a desirable region for a semiconductor to go into. Okay, and you can see from the diagram that in fact this shape will tend towards that of the Ni curve. Okay, this Ni is kind of like the intrinsic concentration, the band-to-band generation number. Okay, you tend towards that because the donor doping becomes negligible in this region. So we call this the intrinsic region. Okay. So, right. So that's essentially what I need to cover for today's discussion. Does anyone have any questions?
So, Prof.
Yep.
When are you? I mean, is like breakdown going to be in our syllabus?
Breakdown. Which breakdown? In this particular case,
like,
or device?
Yeah, device breakdown.
Device breakdown is actually the syllabus. This actually will be covered in the second part of the course by Prof. Ang. When you talk about PN junction, he will actually discuss that particular phenomenon.
Alright.
Okay. Yeah. Alright. Any other question?
Hi, Prof. I actually missed like the first 20-25 minutes because of the whole issue with my account.
Okay.
Can I use a recording that I can watch?
Recording. Okay. I think I noticed like someone starting the recording, right? So Yeah, so if it's actually recorded, then it'll be available for you to review lah. I think the last two lectures has been recorded, right? Did Aaron manage to go in and have a look? Is it there? Nobody checked? Okay, never mind. Yeah, I think later when we finish the discussion, you can have a check lah, to see whether the recording is there.
So I think it is.
Huh? Sorry?
So I think it is
Okay.
the last lecture's recording. Yeah, I downloaded it. I remember.
Okay, great. So you can check it lah. If it's there.
Okay, thank you.
Yeah. Okay. Anything else? Anyone has any other questions?
Hi. Can I ask, are we expected to memorize the energy eigenvalue formula?
Energy eigenvalue formula, are you expected to know it?
To apply it.
Yeah, I mean, if there's a need, you should be able to apply it. If I'm not wrong, I think that the formula list we have put in the eigenvalue equation for you to use if there's a need.
So we do not need to memorize it.
No. If there's a need or the question asked, either we'll give you, or if not, I think that formula list will have it. Okay. So again, I think we discussed the Schrödinger equation and again in today's discussion, and in fact, the energy band structure, the EK diagram, may be something that is quite counterintuitive to you, but the expectation here is that, at least you appreciate the process in which the EK diagram is determined, and appreciate that the EK diagram of an electron in a semiconductor is no longer like a free carrier anymore, which is parabolic, but instead, near to the conduction band edge and the valence band edge is actually still approximately parabolic, which means that we can actually treat them like classical particles, and analyze it using classical formulas. Approximately, that actually helps to simplify the analysis. Except that this parabolic characteristic, right, is actually not equivalent to the rest mass of the particle. Okay, instead, it's a sort of effective mass quantity, because in the EK diagram it takes into account the interaction with the atoms in the crystal. Okay, so if you kind of understand and appreciate that, that's probably good enough already. All right.
Hi, Prof. Yeah. I'm Alistair from Hwa Chong. So I have a question about when you calculated the binding energy, the donor binding energy for gallium arsenide.
Yes.
Yeah. So may I know why you use n equals 1? And why why not n equals 4? Because I thought arsenic, the valence shell should be principal quantum number 4, right?
No. This in this case, you see, when we find the possible energy state of this fifth electron, right? We find that it has a range of values that it can have. Okay, so at sort of ground state, where the fifth electron is actually not having any thermal energy, you will expect it to sit at the lowest energy possible, which is n equal to 1. So that's the lowest position that it sits. And in fact, this lower position corresponds to the donor level. So for it to get to the conduction band, it has to go all the way up to n equal to infinity, right? Once it reaches infinity, then it's free to move, which corresponds to a position in the conduction band edge. So the kind of binding energy will be the difference between the value of n equal to infinity and n equal to 1. Okay, so it has nothing to do with this n equal to 4, right, the quantum state, because this is not specifically well, I mean, in this case, it's just a single free electron, the fifth electron that is freely bound. Okay, so there's only one electron effectively, so it should sit at the lowest level possible, n equal to 1.
Oh, okay. So on top of that, it's also like based on the premise that we are at 0 Kelvin.
Yeah, correct.
Oh, okay. Then I have a second question, which is, if for donor atoms we have a math representation for the difference between EC and ED, then is there a similar representation for acceptor atoms, which is the difference between EA and EV?
You can probably sort of similarly. Okay, actually in that case, the acceptor one is a little bit harder to derive because it's the absence of an electron. So to derive that energy separation, it will be a little bit more challenging. In the case of the donor one, it's easy because there's a sort of equivalent representation, right? The fifth electron is like a hydrogen atom, right? It's like a hydrogen atom model that we can use to represent, and from there we can infer. Whereas in the case of the acceptor one, it's a missing bond, right? Which there isn't an equivalent model that you can use. So theoretically speaking, you can derive if you apply Schrödinger equation, but it'll be challenging lah. But anyway, that's not in the. There will all be something that we tested.
Okay, thank you very much.
Yeah. Sure.
About the charge particle equation, are we supposed to use it to get answers during the exam?
The charge particle,
the neutrality equation, sorry.
Yeah. Will you get an equation?
Will we be asked to use it, apply it in any case?
Oh yes. In fact, subsequent lectures we will start to use it to do some calculation. And if I'm not wrong, this equation will also be provided in the formula list.
Alright, okay.
Yeah.
Thanks.
I think it's critically, not critically now. I mean, it's also sort of essential that you understand how the equation come about, right? So that in a case where you do not have the equation, actually you can derive it, right? If you go through this analysis, you can actually write down the charge neutrality equation, right? If you understand where it comes from. Yeah. So I think, of course, other than relying on the formula list for the equation, right? I think the other part is the understanding in terms of some of this equation, how they actually come about.
Alright. Yeah, thank you.
Okay.
Hi, Prof. I have a question as well. So, it's similar to the person before him. When n equals to 0, shouldn't E infinity be equals to infinity instead of 0? Because
when n equals to
0.
When n is equal to 0?
Because you are taking a number divided by 0, shouldn't that be infinity?
Oh no. In the solution, right, of this energy eigenvalue, the n starts from 1. It doesn't start from 0.
Oh, I see.
Yeah. The solution value for n is start from 1.
I see. Could I also ask, as for the well diagram, the one where is then how can I ask? How is it that you can make a curve into a straight line and?
Okay, it's not about making the curve in a straight line, because of course, strictly speaking, if you want to solve it strictly and accurately, you should use that 1/r relation, right? But if you have to do that, then it's quite complex to solve. Okay, so in order to better understanding in terms of how the different parameters affect the band structure, what we can actually do is to make an approximation. Okay, so what we're doing is actually making an approximation. Instead of using that actual 1/r relation, if we say that, okay, this kind of look like a shape of a well, right? And instead of using that 1/r, we replace it with a rectangular well, okay, which has the benefit of making it easy to solve, because in each of that well region, it's constant value. And if you put it into the Schrödinger equation, it's a lot easier to solve. And in fact, you can, in a lot of cases, you can get analytical expression, which will tell you, specifically what parameters will influence the solution of the band diagram. And this actually gives you some insight in terms of how the different parameters of the crystal affects the band structure. Okay, that's basically used under that premise. So it's more an approximation. so that you can get analytical expression.
Oh, I see. Thank you.
Okay. Anyone else? Anyone has a question? No? Okay. Yep. Yep.
I'm the person from before. Can I ask as for the well, it's 0 to A, right? Could I ask what does the A refers to?
Oh, the A, you can just think of it as a representative dimension that approximate the well. So you can think of it as like a sort of average distance that you will find the electron in.
Oh, okay. Thank you.
Okay, if there is yes.
I give 2 questions. Firstly, when would the second tutorial be out? And second question would be for next week's lab, is there anything we must bring apart from our writing materials and maybe pen and paper?
Okay, the tutorial I think should be out already. I've set it to release after our lecture, so you should be able to download it soon. And for next week's lab, I'll also be putting up the lab manual for you to download and print. So you're expected to print and bring your own lab manual. Okay, so that will be up soon. Okay. Since everybody is here, right? In fact, for next week's lab on Wednesday, for those who are on the Wednesday lab session, I may have to sort of shift that lab to maybe the following Wednesday. Anyone have issue with that? Because we have a sort of upcoming sort of school event that I have to sort out, so I may have to shift the lab. For those who have been scheduled for next Wednesday, are you able to make it in the following Wednesday? Anyone has issue doing it in the following Wednesday?
Yes, I'll have issue the following Wednesday.
Okay, I see. Okay, right. Anyone else or just one person?
Me too, sir. Me too.
Okay, following Wednesday also have problem,
Yes.
Yeah, me too.
Okay, right. Okay, never mind. Maybe I'll put up some survey to see whether there's any other common slot that we can find, and let's see whether we perhaps may have to shift it now. Okay, anyway, let's do this offline. Okay, any other last question before we end the session?
Prof.
Yep.
Just now when you were talking about the impurity saturation, it got a bit too quick and I didn't catch.
Okay. Yeah, the impurity saturation basically refers to the case where all the dopants are ionized. Then that corresponds to the impurity saturation condition. Okay, because it's sort of the ionization saturated already. You can't ionize anymore because all of them has been ionized.
Hi, Professor. Can I ask, how far can you dope the semiconductor before it loses its semiconductor properties so that it's not acting like a metal?
Yeah, that's a good question. Okay, I'm going to leave it as a sort of thinking point for everybody, right? And in the tutorial class, we can discuss about it. Are you in my tutorial class?
I don't think so. I think I'm in Professor Ang's class.
Okay. Then, what you can do is during the tutorial class, you can raise the question. Okay, but at this stage, I'll let you guys to think about it. What do you think is kind of the maximum dopants you can put in a semiconductor, right? So that it still can be considered as the particular semiconductor instead of changing it totally. Okay, so I'm going to leave it as something for you to think about. Thanks for the questions. It's a good thinking point because you think through, I think it sort of tests your understanding of this doping. Okay, think about it. We'll discuss in class.
One more question, just to confirm. The more dopants you add, the longer the extrinsic region will be for a specific material, right?
The more dopings you add, the longer the extrinsic region.
Yeah, as in, if you look at the electron density against temperature graph, the extrinsic region will increase, as in it will be longer.
Extrinsic region will increase.
As in, because the amount of
increase
or would it be the freeze out region that increases?
Increase as in it go up or what?
As in wider, it becomes wider.
Okay. Actually, I will also discuss this in tutorial class. So, good question. So everybody go and think about it. What happens when you increase the dopant? How do you expect the temperature profile to change? Okay. And for those in Prof Ang's class, you can ask a question if he doesn't cover it.
Prof. So Professor Ang introduced in-gas and out-gas during the previous tutorial. So the one has 3 different elements, and how would it differ from 2?
How will it differ from 2? The addition of another element. So typically, if you look at in-gas, right, the material will have indium, gallium, and arsenic. Okay, so the indium and gallium are group 3 elements, and what you find is that depending on their ratio, proportions that are in the semiconductor, you will have them in alternating position. So essentially, they'll be like uniformly distributed throughout the crystal. But in terms of the semiconductor behavior, it's largely the same as, or very similar to this 2-element compound semiconductor. It's just that instead of gallium, in some position you have indium, which is still group 3. So these slightly different elements actually affect the band structure of the semiconductor, and you can use that to adjust the band structure to suit your need.
Right. Okay.
Yeah.
Hi, Prof. Could I clarify if we need to understand what is photon?
What is?
Crystal momentum.
What is crystal momentum?
Crystal momentum is the.
Sorry, you're saying whether you need to understand what is crystal momentum?
As in cause when there's a change in crystal momentum, you need photon.
You need what?
The PHONON.
Oh, phonons. Okay. So the phonons are essentially sort of a representation of the energy of the vibration of atoms in a crystal. Okay, so the atoms in the crystal is vibrating, right? All they are vibrating in different directions and all that. So we call this modes. Okay, and this vibration, if you were to calculate, right, you can find a description for this vibrational energy. Okay, this vibrational energy are, we think of them as like packet of energy, like photons. Okay, so this vibration energy also can be thought of as like packet of energy. We call them phonons. Okay, and when we do analysis in semiconductor, right, a lot of times we treat it as a particle, so that when it interacts with particles like electrons and holes, we just analyze them using particle sort of interaction. Okay, which makes it easier to describe. Okay, so that's the concept of phonons. So just now we talk about indirect bandgap semiconductor. The electrons can come down to the defect states, right? Either that or they go directly to the valence band. But in order to do that, you have to get some relevant for momentum. Okay, to make the conservation of momentum condition. So this additional momentum I mentioned can come from the vibration of the crystal lattice. So in other words, we can think of it as if the electron can find a phonon that allows it to conserve the momentum, then it can transit from conduction to valence band. Then it can emit a photon. Okay, so in this description, we kind of visualize the vibrational energy as packet of energy of vibration, the phonons. Okay, that's what phonon is. It's essentially a packet of vibrational energy.
Oh, I see. Thank you so much.
Right.
Yep. So, will we be tested to draw the EK diagram?
The EK diagram, yeah, possible. So, specifically in the context of describing what is a direct bandgap semiconductor. So you must be able to draw the correct diagram and explain. Okay, that's usually mostly what we need you to be able to do.
Oh, so does the diagram need to have like specific points with the peaks and the minimus and maximus? Must it be in a specific region?
Okay, so if you are asked such a question, you just need to draw some representative diagram, with the correct feature for direct bandgap and indirect. So if you do not remember exactly for gallium arsenide is straightforward. For silicon, if you do not remember exactly which position on that, just do a sketch on that's good enough. So in other words, you don't have to label specifically where is the minimum point on the K value, right? So we don't need you to do that. Yeah.
Professor, can I ask you, how do we dope binary compounds like gallium arsenide since they already have good size?
How do you dope it?
Yes.
Okay, the doping can be done in many different forms. Okay, so one way is when you make the crystal, right? In the melt of the crystal, we put in the impurity atoms together. Okay, so that when you form the crystal, it's embedded in the crystal already. Okay, that's kind of one way. But the more common way that's being used is that, okay, given a semiconductor wafer, for example, instead of dope a certain part with phosphorus atom, for example, then the current practice, right, is to put the semiconductor into a chamber, and then they basically vaporize phosphorus in the chamber, and the phosphorus atoms, right, would basically be present on the surface, and because it's maintained in some heated environment, the phosphorus atom can actually diffuse into the crystal. And how deep it diffuse, it can actually control by varying the temperature condition to achieve a certain depth that it go into. Okay, so that's one way to dope some part of semiconductor. Of course, the other part that you don't have to dope, you have to put some what we call resist to cover it so that the atoms doesn't go in to that part. Okay, so you can selectively dope different parts of the semiconductor. That's one way. Another way to
sorry, but what I mean is if you want to accept the impurity for gallium arsenide, how do we then, or what atoms do we actually then insert into the semiconductor?
For accepted impurity in?
Let's say for gallium arsenide,
okay,
this already has group 3 and group 5 atoms. What atoms do we use to dope it?
Okay, for elements like that, it's okay, gallium arsenide, if you want to dope N-type, we put silicon. Okay, and if you want to put P-type, we can put boron as well, So the mechanism in which it forms the donor and acceptor, right, would depends in such case, and usually we can calculate by doing this Schrödinger equation calculation. So you can actually work out to see whether if you put in a specific element, is it going to give you donor atoms or acceptor atoms in the semiconductor. So specifically for gallium arsenide, for N-type doping, we put silicon, right, which is a group 4. For P-type, we can actually put boron into it. So different semiconductor, it may require different ones. So this requires you to actually study and do experimentation to find out which are suitable dopants in those semiconductors.
Oh, okay, I see.
Okay, If there is no more question, then
sorry, Prof. I'm sorry. So going back to Alistair's question just now, he asked why the energy required to propel the electron of K1 arsenide to the conduction band is using n equals to 1, right? So why are we making the assumption that n is 1, or rather is always at the ground state?
Because in the case of this fifth electron in the loosely bound to the phosphorus atom, right? That's the only electron, and under condition where there's no thermal energy, it should sit at the lowest level, which is the n equal to 1 state. Because in this model, the fifth electron is like a hydrogen electron, okay, and that's the only electron in that model. So if you have so much different states and there's no thermal energy, naturally the particle will sit at the lowest position possible.
I see.
Which is n equal to 1.
Why would we assume that there's no thermal energy at all, like K equals to 0? Because in everyday applications, isn't K like a few hundred?
Yeah. So when we talk about binding energy, we're talking about the lowest energy possible when T is equal to 0. Of course, at room temperature, naturally you will not expect the guy to sit at n equal to 1, right? Because with thermal energy, easily they can go up very quickly. And that's why at room temperature, you'll find the electron, right, in the conduction band instead of in the donor level. So basically, the binding energy gives you an idea of how much energy you need to give it for it to get to the conduction band. So that will be essentially like the maximum energy that you need to give. So we take reference to 0 Kelvin, which is n equal to 1. That's where the electron will sit.
Yeah, thank you.
Okay. If there's no more question, I think we can end this session. All right. Okay, so I'll see you guys.
Sorry, one last question.
Yeah, go ahead.
Which is earlier when you mentioned about the reduced K space and the different forbidden energy bands.
Yes.
Based on my understanding, the energy band that we are concerned with the most would be the one that corresponds to the valence shell. That is the one with the conduction band and the valence band. And all those forbidden bands that come from, let's say, the 2s or the 1s subshells, those should correspond to the forbidden energy bands that are lower down on that diagram which you showed us.
Are you talking about the EK diagram?
Yeah.
Okay.
I wasn't very sure why there were so many forbidden energy bands.
No. There is. Okay, so first of all, you need to understand that this. Okay, let me just try and. Okay. I think you're talking about this, right?
Yeah. This
okay. Okay, so I think you may have mixed up this with the one where you show the energy splitting and eventually they come to equilibrium, right? This two graph is different. This is E against K, energy against momentum. The other graph is energy of electrons versus separation between the atoms. So in fact, this energy states here, right? Okay, this part here, right? These two curves are actually the valence band, and this two part corresponds to this and above correspond to the conduction band. So there's no sort of connection to the other graph that we were showing. You know what I mean? So this doesn't relate to the lower like 1s, 2s.
Okay, I see. So it just represents that somehow
just the 3s and 3p.
At those momenta, potential energy is unattainable.
That potential energy,
like those forbidden bands. Yeah, so those forbidden bands in this case, it just refers it doesn't exactly refer to the band gap, but it just refers.
You mean here? Yeah. No. This is just no. It's not specifically the band gap already, because the electrons would essentially have states that's here and here, right? So the band gap is actually here between the empty states and the filled states.
Okay.
Yeah. And so the bottom one is
So the reason why those other forbidden energy bands exist is just because the Schrodinger equation says so.
Well, I mean, it's because of the interaction between the atoms and that resulted in this kind of structure.
Okay, yeah. So like, it's impossible for it to attain those potential energy values in the forbidden band.
So you're saying that the electrons will not have some energy in between here?
Yeah.
Yeah. Sort of lah. Yeah, you can think of it that way.
Okay, thank you very much.
Okay.
Professor.
Yeah.
For this slide, does it mean like if there is a scenario where all the electrons in the valence band is excited into the conduction band, means some electron need to overcome two forbidden energy bands.
Sorry, say that again.
If all the electrons are to be promoted into conduction band, meaning some of the electrons need to overcome two forbidden energy bands. Meaning one is like below, and one is the energy band in the semiconductor.
So you're talking about those that is here lah, and then they have to cross these two, right?
Yes.
Yeah, that's correct.
Okay.
Yep. But in reality, just to add that in reality, a lot of times in practical application, the transition of electrons typically occur around this region only because the density of electrons in this region is very large. In this region, just the parabolic region is very large. Unless you are able to excite so much electrons that it affects all those that is deeper down, right? If not, most times practical application is just this region. So we just need to be concerned with this. The other parts actually, most times we don't really need to consider. Okay. Right. Okay, so I think we would stop here. So just go back and think about it, read through, try and understand again. If there's any questions during tutorial class, you can ask again, right, or clarify. And that's all we have then. Okay, thanks very much. I'll see you guys next week then.
Thank you, Professor.